All right, welcome back everyone to our sequence on mechanics of materials. And this video is going to be about composite beams or beams with cross sections that are composed of two or more materials. And something like that would be if you've ever ridden a skateboard or if you looked at a skateboard, you might have seen that a skateboard has various layers of wood that are bonded together. Okay, so that's really a composite. Or maybe you've used like a snowboard or something that's or a surfboard even that has a glass epoxy on the top and bottom right here, a glass composite, and the inside is a foam core. Okay, a foam core for a surfboard, and this is a popular configuration for lots of other kinds of other materials and beams, right? Trying to take advantage of the expensive material at the top and bottom to take a lot of that normal stress due to bending, and then the middle, the foam core is really of low value when it comes to normal stresses, and you just really need to take up the shear here. The Another example might be reinforced concrete. You got concrete with a layer of steel somewhere, so this would be a composite beam. You got all kinds of examples, or maybe, gosh, if you're taking like a composite materials course, like on fiber reinforced polymers, you might have something with, like a glass epoxy layer on one layer, and then a carbon epoxy layer, and then another glass epoxy layer, and then something in a whole different orientation. But you have all these different layers of material in a composite material. Okay, and it doesn't matter what the material is. What is different though in each layer is that the modulus of elasticity, changes between materials. They're of different moduli. And what we want to do in this video is talk about how to really analyze them so that we can calculate stresses due to bending. And one of the ways to do that is this thing called this transformed area method. And we'll talk about how to do that and then how that helps us calculate normal stress due to bending in a composite section. And really, the idea of the transformed area method is to take this section of multiple materials and transform it all into an area with an equivalent one single material so that you can use this sigma equals minus my over I z, right? You can use this flexure formula to calculate your normal stresses. So let's take a look at what a composite beam is in a little bit more detail. And a composite beam here, so let's just take a beam that has two layers. Um, so here, if I looked at the length of the beam, let's take for instance a beam here. I'll just draw a beam here, and it's got two layers of material. I don't know exactly where it divides unless I design it, but it's got two materials. So this is like material 1 and material 2, simply supported. It doesn't matter what the support is, and then with some sort of loading going on it, and I'm just saying it's some loading, and it just happens that I draw a uniformly distributed load right here. But if I look on the inside, if I make a cut and I look at the section, if I make a cut and I look at the section, and if I draw this section here in a little bit more detail, maybe this is what I see. I see two materials. I'll say material 1 in like, how about purple for material 1. So here, I'll say here, the first material on top of it is here, and it looks like this, and then it's bonded to another material, which I will put in, let's say, like a green, like a light green right here. And let's say material 2 is bonded, so I make this funky cross section right here. Bam, like this, right there. I don't like that green. That green's a little too light for my taste. So here, let's do a little bit darker right there, here, and here, right there. And let's say it's got some dimensions. Let's say the dimensions are here. We'll say that this dimension right here is this dimension. We'll call this B1, the width of material 1, B1. And then this is the height of material 1, right here, H1. Here is the height of material 2. And here is the width of material 2, right here. And I'll just call that B. Okay, I'll just call that B right here. And this is material 2. It's got modulus of elasticity E2. And this is material 1. and it's got a modulus of elasticity E1. And we'll say that E1, or material 1, is stiffer than material 2. So it would be like, this is steel, and for whatever reason, this is concrete or wood or something, right? Something you bonded together, okay? And so here, if I look at this in a composite material, if I look at the strain profile of a composite material, right here, and assuming none of the materials have yielded or anything, right here, this strain profile, something you can always hang your hat on, is that this strain profile is linear, okay? And here I'll call this compressive strain, and here this is my tensile strain. Here we'll say that the moment here at this cut looks like this. Whoa, let's put it over here on this side, that way there's no confusion right here. So that's causing compression at the top, tension at the bottom. I really don't know where my neutral axis is, but I do know that it's at the location of 0 strain. So here, 0 normal strain. So here's my neutral axis somewhere down the road, bam, like this. And then we'll call this distance some distance from the neutral axis to the other end. I'll call that distance C, okay? It's not necessarily the maximum distance, but it's just the distance from one end to the edge, from the material neutral axis to the edge here. And the stress profile here, if I look at the stress profile, the way I would get the stress profile is, if I know the strains here at each of these locations, then I would apply Hooke's law, which is, sigma. So this would be my strain profile. I will go to Hooke's law, which is sigma is equal to E times epsilon, and I would get my stress profile, my stresses. And so here, for this, all the way up to material 1, material 1 goes all the way to this point right here. Okay, so bam, up to this point right here. I'm going to have compressive stresses here that when I multiply here, I'm going to take every one of these strain values and multiply it by E1, or capital E1 here, because I'm in material 1. And so this will look like this. This will be like this. Oops, not arrow going that way. Let's see, edit, undo that ink stroke. Yes, good. And then here I'll have stresses like this right here. And this would be my stress here at the top here. The sigma, I'll call it sigma compression, is equal to E1 times epsilon compression right here. And then same thing here, all the way up to this point, I'm going to have tension below the neutral axis. And every single one of these points here, I'm multiplying by E1. So up to here, I'm multiplying everything by E1 again, this capital E1. And so this has, again, this is, E1 times the strain value here. And then all of a sudden I get to material 2 right here. And material 2 has a smaller modulus of elasticity. And all of a sudden what's going to happen is, because I have the same strain value at this point right here, but I'm multiplying by different or lower modulus of elasticity, I'm going to have this discontinuity. I'm going to have this step where I'm going to be here. My stress value may drop down to here, and then I will continue linearly all the way down to here like this. So here, and the challenge with analyzing composite materials, and this would be sigma tension right here, and this is essentially E2 times the strain and tension at this point down here, is that the challenge with analyzing composite materials is you have these discontinuities and stresses, and that makes this flexure formula no longer applicable. You can't use it anymore. I'm going to stop here for now because I'm getting up to this 10-minute time limit. And anyways, I give you a background on composite materials and the stress strain profiles. So if you like what I'm doing here, then in the next video I'll describe the transformed area method and give you some background on that as well. And then we'll do another video with an example problem or something. All right, hopefully I'll see you in the next video. Bye.